This is a summary of the paper, a hyperfast second-order methods for distributed convex optimization. In this paper, we studied a problem where we have a set of n training samples that is partitioned among m machines. Each worker j has the dataset d sub j available in memory. The objective is to minimize the sum induced by the whole dataset. If we assume the objective function f is strongly convex and smooth, then accelerated proximal methods can find a point that is epsilon away from optimality in the number of iterations proportional to square root of the condition number, where at each iteration, the algorithm needs to solve a proximal step iteration. In the distributed setup, the central node holds a value xt. This value is sent to the workers, and each worker computes the gradient of the local function evaluated at that point. Those values are sent back to the central node, which aggregates them to compute the total gradient. Finally, a proximal step is taken to compute the next iterate, and the process repeats. Recently, Hendricks et al. Proposed statistical preconditioning as a way to accelerate distributed optimization methods. In this setup, the workers are assumed to have similar losses, where similarity is defined by closeness of the Hessian of the both local functions. If the number of training samples n is large enough, then the Hessian of the total loss will be close to the Hessian of the local function and is inversely proportional to the square root of n. If one further assumes that the central node holds in memory a subset of the data points, one can define a function phi from which the total loss f is relatively strongly convex and relatively smooth. Moreover, one can define a proximal iteration with respect to the generated Bregman divergence. This generates an algorithm that converges as the square root of the condition number, but in this case the condition number is scaled by 1 over square root of n, which can be made much smaller, paying the price of higher iteration complexity. The main drawback of this approach is that at each iteration one needs to solve approximate stuff. However, any optimization algorithm will find approximate solutions only. Then one might ask, what is the effects of such approximation? We propose an algorithm that takes into account the inexactness of the proximal steps. Moreover, we can control such inexactness to obtain the same convergence rates. And we solve the auxiliary subproblem using the hyperfast second-order methods recently proposed in the literature. Therefore, at each iteration, one needs to solve an inexact Bregman proximal step, and this in turn is solved using hyperfast second-order methods. We propose and analyze an inexact statistically preconditioned distributed optimization methods. We explicitly characterize the approximation by which the proximal step needs to be computed. We provide a novel hyperfast second-order method to solve the auxiliary problem, which is uniformly strongly convex, and preliminary large-scale numerical results are presented. Please see the full paper for more details.